Walt McClay. I'm going to talk about 5G and we'll learn what it can really do. So first I'm going to talk about the promise of 5G. A lot of things you've heard. And then I'll talk about the technology. And the technology will help us understand what the limitations are. There are 3 different frequency bands with different speeds, distance, and latency. And there are 3 different use cases. The use cases are for cell phones, they're for very low latency, high reliability, and then they're for things like the IoT. And they're very different. And then we'll talk about what this means for the future. What's 5G going to do for IoT? What carrier choices will you choose, and they'll make a big difference. And where you are will make a big difference. So 5G promises very high bandwidth, very high reliability, and low latency. Latency is the time from when you do something to get a response. The enhanced throughput, they claim up to 10 gigabits per second, always on availability, and reduced latency, which I'll talk about several use cases. So there'll be 3 use cases. This is one, virtual reality and augmented reality, which could be used in home or could be used in factories and surgery and many different applications. Right now, the lower end of this, the 1 megabits per second, 2, 20, even up to 50 megabits per second, you can get in 4G. The higher speeds, you cannot, and this will open up in 5G. At the very highest, with up to 5 gigabits per second and low latency, this would allow you to turn your head in any direction and have the display update instantly so that you wouldn't even notice that there hadn't been anything there before you turned your head. You can't do that now, and it takes very high speed to do that. Another use case is in healthcare. There's a number of things that can happen. We'll be able to monitor the population better. You can do this with 4G, but 5G promises to improve it. Monitoring the health of the population has become very important these days, in particular for early medical intervention. And this will be done by having wearable devices, IoT devices, and simply by monitoring what's going on the phones. So we'll have better patient outcomes. One particular interesting area is remote robotic surgery. Now, I've been hearing about this for years, and I don't even know if it's being done at all. It's very rare. With remote robotic surgery, you need to have a very reliable connection. You can't afford to have it fail. And you need to have very low latency so that when the doctor moves his hand, the remote instrument moves, and the feedback is seen instantly, so there's no delay, because a delay makes it very hard. So this is ideal for 5G, but we'll learn about some limitations. And then the third case is smart transportation. There's technology in 5G that will allow and actually make it work very well to have communication along a roadway. This will allow smart vehicles to communicate between each other and with the road. And it can also be used in railways and they say airfields, but we'll see about that. So this could allow things like looking around the corner or controlling the flow of traffic to make it work better. So 5G promises a lot of improvements over 4G. 4G is up to 150 megabits per second, and they promise up to 10 gigabits per second on 5G. Latency, instead of the 50 milliseconds of 4G, down to 1 millisecond. And a lot of this is possible by using new spectrum, up to 86 gigahertz. There's a promise for a 10-year battery life. Now, anybody who understands electronics realizes that all of these above things aren't going to happen simultaneously. At 10 gigabits per second and using an 86 gigahertz band, you won't have 10-year battery life. So you'll begin to see some limitations here. There'll be far more connections in the same space using 5G, and with a higher bandwidth and highly directional antennas, they claim 100 to 1,000 times more connected devices in one cell tower area. So you'll have very high speed capacity, lots of data, and you'll have fewer dropped calls because if you take the more capability for more connections, you'll have less cases where there's no connection when you're trying to go from one tower to another. There's also better security than 5G, than 4G. So that's a very topical item that's becoming more and more important. Now, from here on, I'm going to talk about what the reality is, because the reality is more complex than what's been advertised. You have different capability depending upon the frequency bands. So I'll talk about the different frequency bands. At the very high frequency band, the distance the signal travels is very limited. There are different use cases, 3 different use cases that I'll talk about that are very different. And then some of the capabilities are not yet available. There's also 2 different standards for 5G. They're very similar, and so far I haven't seen any problem with having 2 standards, but it's just something to be aware of. It appears that all the equipment can satisfy and operate on both. But the work is continuing on the standards, so we haven't finalized what 5G is going to be. So let's start by talking about the 3 key frequency bands. There is the low band below 1 gigahertz and the 1 to 6 gigahertz mid-band, both of which have been available using 4G, and 5G will use the same bands primarily. So in the low band, it has very good coverage for urban and rural areas. It passes into buildings very well. You get speeds as high as 100 megabits per second, which people have found to be revolutionary compared to 3G. It's used by carriers all over the US. This bandwidth is very heavily used and there's not much left, but it will be converted to 5G as the 4G use drops. The mid-band, you've got peak speeds up to 400 megabits per second. So this is substantially faster than what 4G has offered before. In this band, penetration of buildings is not as good, though because you probably haven't noticed which band you're on when you're using your phone, you may not have really noticed the difference. Now, new with 5G is the 6 to 86 gigahertz band, or it's often called the millimeter wave band. This is a spectrum that hasn't been used for phones before, and it's primarily in the 28 to 39 gigahertz range. The promise is up to 10 gigabits per second. I haven't seen it get that high. The biggest problem with this band is the penetration. It does not penetrate buildings at all. It's blocked by walls, by windows. It doesn't get into the car. It's blocked by trees, rain, or snow. So you can see that there's a significant limitation. You may have a cell tower very close to you, but you go inside and it doesn't work, or you get in your car and it doesn't work. That's a significant limitation. And if it's raining or snowing, the signal goes down a lot. So to look at these different bands, and we've divided them up into 4 groups here. The high band, the distance the signal travels is less than half a mile. In fact, it's substantially less. The numbers here for miles are optimistic. The low band at 20 miles, that can happen, but it doesn't always happen that well. So you'll get less than these distances. You can get up to 2 gigabits per second. This is the capability that I've seen in the high band, and 50 megahertz in the low band. And the latency also depends upon the band. The very high band will give you the 1 millisecond latency. It's going to be more like 30 milliseconds on the low band. So the band you're in makes a big difference. And now let's talk about the 5 different service classes, or sorry, the 3 different service classes for 5G. The first one at the top is eMBB. enhanced mobile broadband. This is the cell phones and tablets. This is what you've been used to. And it's going to give you much higher data rates, much more dense devices per unit area, and lower latency. On the lower right is the ultra reliable low latency communication. This is where we talked about for remote surgery, for use in roadways. So I'll cover that one. And then on the lower right, the massive machine type communication. This is, excuse me for the interruption. This is basically IoT, massive machine communication. And this is a very different type of application. So let's talk about the eMBB, which is the cell phones and tablets. The data rates can be up to 2 gigabits per second, which is 20 times 4G. That's very significant. They claim you can have 1 million devices per square kilometer. That's a huge number. Even if you can only approach a fraction of that, that would largely solve the problem of dropped phone calls. And it will allow for some very interesting things in the future, like a stadium full of people all getting very high speed communication. Now, as I talked about before, the band makes a big difference. So if you're in the sub-gigahertz band, you're going to get 100 megabits speed going up to the cloud and 50 megabits down. This is similar to 4G. So in that band, not much change. In the 1 to 6 gigahertz band, up to 400 megabits, which is substantially more than 4G. You'll notice the difference, but it's not the 2 gigabits. And then in the 6 to 86, the millimeter wave band, you will get the full speed. But because of its limited distance, it's only going to be available in dense urban areas. I don't see this being available in even suburban areas. Right now, if somebody wanted to put a new cell tower in your neighborhood, it probably wouldn't get approved. And it would require a cell tower approximately every 100 meters to give you full coverage. So this is going to be limited to only certain areas.
A question, Walter, for the previous slide, and you mentioned the below 1 gigahertz band up to 100 megabit per second down and 50 megabit per second up. What is the signal bandwidth was used in this calculation?
I don't know. This is similar to what the bandwidth is. I haven't paid attention to the bandwidth because what's important is the sample rate, the data rate. But the data rate and the bandwidth are related and they're similar.
I see. Also, the 100 megabit per second, this is per sort of a sales station. This is a total throughput, not the average throughput. Is that the correct assumption?
This is the throughput for one device. So now when they tell you that you're going to have 1 million devices per square kilometer and they're going to be at 400 megabits per second, I don't think that's going to happen. That's an incredibly high speed, but I don't think we're going to see 1 million devices per square kilometer anytime soon. So there's another limitation. You will get very high speeds with a lot of devices in an area. Mm-hmm. This is done by having directional antennas. So you can have the whole set of frequency band available in each different direction.
Mm-hmm. Yes, okay, thank you.
Okay, now let me talk about this new use case, the ultra reliable low latency. This is mainly for use on premise. This is where somebody sets this up for themselves, not a publicly available cell tower. So I've listed 4 scenarios. One is discrete automation, another is process automation. These are similar. This would be in a factory. You notice on the right, the service area is, in one case, 100 by 100 meters, a very small distance. This is a building, basically. It's going to be able to give you low latency, like 1 millisecond, very high reliability, and pretty reasonable speeds, but the very high speeds are not so important. But if you combine a large number of devices in one area, a terabit per second per kilometer squared is a very high density, but the point is it doesn't cover a kilometer squared. It's 100 by 100 meters. So it doesn't give you a terabit per second, but it's very good speed. So this will be done by somebody putting a cell station in a factory, for example. Another one is
Walter, another question with regarding the high reliability here. Now, in wireless link, typically there's a very prone to physical layer interference.
Yes.
And are those reliability factor into in an interference in environment, or it's an interference-free environment?
Give me a couple slides and I'll talk about the reliability. Yes,
thank you.
It's an issue. And you're right to say that that's a surprisingly very good number. So look at the third item, electricity distribution. This is for use along power lines that will allow the power company to monitor what's going on in the power distribution. So this is along the power line up to 200 kilometers, but this would not be something that you would connect to with your cell phone. And then intelligent transportation, we talked about having vehicles controlled with 5G. This would be up to 2 kilometers along a road. And again, this is not designed for pickup by your cell phone, it's designed to be picked up by your car. And the speeds are pretty high at 10 megabits per second, but not astounding. Latencies are quite low. So these are some use cases that are very different. This has not been offered before in 4G. Now there's some limitations.
Before you go to the latency, we have an anonymous question regarding how much of the latency improvement comes from use of the high frequency bands, and then how much of the latency benefit do you see on low and mid band 5G?
So you may have remember the earlier slide with the triangles. You get the low latency really good at the very high frequencies in the millimeter wave band, and only a modest improvement in the low band. And I'm going to talk a little bit more about latency. There's some issues here. So a big limitation of the ultra reliable low latency is that it's for use on premise. It's not available for everybody, for your cell phone, for example. It's typically installed by a company or factory or roadway or utility. The latency is only one direction. So when it says 1 millisecond latency, that's going from the transmitting device to the receiving device. It's not two directions. It doesn't include the return trip. And in many cases, what you're interested in is I send a message and I get a response. So double the latency. It also doesn't include the delay in the internet itself. So if you're traveling anywhere besides from one part of a factory to another and you get on the internet, there are delays for every switch that you encounter, perhaps a millisecond per switch, and you can have many switches. So the latency can be much higher, though keep in mind this for URLLC, this is on premise, and you're typically not going to the internet. The communication is more reliable than 4G, but I'm going to talk about that in just a moment. So what will improve? Well, one thing that we can do about 5G and the millimeter wave band is have picocells. So I said that the signal won't penetrate windows, it won't be indoors, it won't be in cars. You can overcome that if you put it in a picocell. This is a small cell that will have an antenna outdoors and bring the signal indoors. You've seen this with 4G. You can buy a picocell that fits in your hand, and you could set it up, for example, at a trade show where there's so many people using cellular that you can't rely on it, and you set up your own, basically your own tower, your own cellular setup. If you do this for the millimeter wave band, you would have to have one device in every room because it won't pass from room to room. And having it in a car, I haven't seen those yet. There are picocells available, but they cost $500 to $1,000. They're not widely available yet for 5G. Now, with 5G and on-premise, you'll be able to have a stadium that has the millimeter wave band, and everybody could receive it because you can set it up how you want. Or it could be an entertainment facility. So you could give people the very high speeds when they're all together in some kind of entertainment. I don't know what would come from that, but interesting things are bound to happen. And then we talked about the roads, the factories, and the power lines. That's new. That's going to be changing things. The high density of connections for 5G is going to be a big boon with fewer dropped calls. I'm sure everybody gets very frustrated when they're in their car and the call drops. And sometimes even when you're stationary and the call drops, that should be a lot less. And then 5G has much higher security than 4G. So what kind of things are unlikely? Well, we talked about the augmented reality and virtual reality. This is fine unless you're traveling a really long distance, and you're not going to get the highest speed in your home unless your home is in a dense urban area. Remember, the millimeter wave band travels a fraction of a mile. You're not going to have it covering the suburban areas. In addition, there's a long delay if you transmit it a long distance. The remote surgery is another one. Where it's most useful is in the country. You want a doctor in a city where there's lots of them to an operation in the country where there's a shortage of doctors. Well, you're not going to have the coverage of the high speed, the millimeter wave in the rural areas, unless they set up their own cell tower. So it is possible that a hospital would put in a remote surgery setup and include the cell tower, and then it would work. Speed is a problem. In the low bands, not such a big change. In the suburban areas and rural areas, basically little change. You'll see the real high speeds and the low latencies in urban areas, and only when they have time and money to build out a very dense set of cell towers. So let me talk some more about latency. The 1 to 10 milliseconds of latency, I already talked about. It's transmitting from the transmitter to the receiver one way. So double it if you're looking at a round trip. To cross the country, it takes 10 milliseconds at the speed of light, not counting the delay for every switch that it sees along the way. So by the time you add up all this, if you're talking about long distance communication across the country, you should expect 20 to 40 millisecond latencies. And this is not a lot different from 4G. And then the reliability. Anybody who expects to get, what is this, 6 nines reliability, this is 1 part in a million. With wireless connections, this is not really going to happen. This is saying that you lose connection 30 seconds out of a year. Well, if the wind blows down a tower, you've blown it for a century. So what apparently they're really talking about is the bit error rate. And the bit error rate is talking about if I send 1 million bits, I lose 1. That's what this means. And that is important because that means that the speed and the latency will be high. If you have a low bit error rate, it will be frequently resending the signal. And when you have to resend, that reduces the data rate and increases the latency. So that appears to be what's really being talked about here. There's some other issues with 5G. We talked about how the signals are blocked by pretty much everything, including your hand. If you put your hand in the wrong place on your phone, it blocks the signal. to give you an idea of the distance that these millimeter wave signals go, see coverages, and they said 100 to 300 feet worked really well. That's feet, not meters, from the base station. They got beyond, so at 100 meters, it was working, and beyond that, not so well. So when I gave 0.6 of a mile earlier, I said that was optimistic. It's very optimistic. And of course, it doesn't pass through a building. If it's not direct line of sight, it doesn't work. Another issue is the millimeter wave band uses more power, both in the transmitter and in the phone. At temperatures, people have measured around 80 degrees Fahrenheit, your phone overheats and it switches either to 4G or to a lower band, and you no longer have the high speed. The base stations use much more power than LTE or 4G, so some people are worried about them not being green. There's also concerns about the health effects of the millimeter wave signals. Now, we used to have this about the lower frequency bands. It's still not 100% clear on what the health effects are of the existing cellular bands, though it is required to limit the amount of energy that's absorbed by the head from your phone. I expect that the health effects for the higher frequencies will be something we hear about for a long time and will never be 100% settled. And then finally, there's interference with weather satellites. The satellites are picking up signals from the Earth. This is not transmitted signals, but they're signals that are picked up from various objects across the Earth, such as from rain. And these new transmissions are much stronger and will interfere, so the satellites will not be able to measure things like rain as well as they have in the past. That may interfere with our weather forecasts. Okay, so I talked about two of the use cases. I haven't talked about the massive machine type communication, which is IoT. So let's delve into that. This is a very, very different use case from the rest of 5G. Low power is important, a long battery life, data rates of 160 bits per second. I don't know why they picked exactly that number, but very low data rates. A large number of devices in an area. Latency, not important. This is 10 seconds, not 10 milliseconds. It's not important. And the hardware has to be low cost. You're talking about lots of IoT devices. So today, 5G doesn't provide very much in this area. The new standards are being worked on. The 5G is optimized for very high speeds, and it's not optimized for very small packets with very short sessions. You can't do both at the same time, or at least I don't see how to do both. Currently they haven't got it. For example, if you want to send 10 bytes of data, right now it takes 100 bytes of signaling to get that sent. So not too efficient. And they're the channel coding schemes. You've got the time is split up into various channels where everybody gets a little piece of the time, this time domain multiplexing. That's not very efficient either. And then the 10-year battery life depends entirely on the application. It only works if you're sending very infrequent messages that are very small. Any device that's sending data every 10 seconds, it's not going to have a 10-year battery life. So what about existing IoT services? There are two important ones, NB-IoT and LTE-M. These have been around for years, and they've become pretty well built out now. They will coexist with 5G. The plan is that they're going to exist for a long time and that existing devices will continue to work for a long time in the future. Even these NB-IoT and LTE-M are not optimized for small data packets, but they work quite well. And the coverage now is good, and the plan, they work for up to 50,000 devices per cell. Not a million, but in most cases today, that's fine. There are also some services that are not related to cellular, but they also will work with 5G. Now Zigbee, I stuck it in here, it's a short distance, it's quite different. But there's LoRa, which has had some people are familiar with. Ingenu is pretty unusual. Sigfox people have heard of, and Weightless, not too well known. These use unlicensed spectrum. So you're not having to pay for airtime or at least as much. I'll get into that more a little later. The availability is an issue. So what's going to happen with IoT? Basically, not much change, at least not for now. Now, the good thing is the change has been happening. NB-IoT and LTE-M have, well, Verizon says 92% of the population is covered. And that was May of last year. That's almost a year ago. And it's been getting better and better. NB-IoT is more widespread than LTE-M, but Mexico has only coverage by AT&T. Neither one is available in India or South Asia or parts of South America and most of Africa. So worldwide, not as good. And will today's devices remain compatible? They say they will. They probably will, but we don't know for sure. So let's talk about availability. In this chart, the purple is where you can have either one, either LTE-M or NB-IoT. The US and Canada are covered really well. And Mexico is starting to get NB-IoT, where it's shown in orange or yellow as being only LTE-M. The blue is where there's only NB-IoT, so some important areas like China. And the gray is where neither is available. It covers all of India, the Middle East, pretty much all of Africa, and some other important areas. Now, this is a coverage map for the US just by T-Mobile. There are others. This isn't bad. This looks only a little worse than the cell phone coverage map. So coverage is pretty good. And that wasn't the case just a few years ago. So this is good news. By comparison, this is coverage of LoRa. Now this is by one provider. This is not good news. If you sold a device with LoRa, you wouldn't be able to use it in most of the country. So let's compare some other things about these. LTE-M and NB-IoT on the left, and then Sigfox, LoRa. And then just as a comparison, I've got Bluetooth LE mesh and Zigbee, which are very different because the distance to go is much smaller. So the data rates, LTE-M can be up to a megabit per second, but it's really not designed to go that fast. But LTE-M and NB-IoT can support audio. Don't try and do video. You'll notice Sigfox is 300 bits per second. Now, it's much smaller than the others, but that's the kind of data rate that all of these are really designed to work well at. And then you'll notice that LoRa is unusual. It can be public or private. In the next slide, I'll explain more about what that is. You can set up your own cell or your own transmitter to provide LoRa in a location. So good coverage for LTE-M and NB-IoT, and the others they're more limited. So private versus public. A private communication or private facility, both ends of the communication you install and you own. So you buy a device that has LoRa, for example, you put in a base station that has LoRa, you own it, and only your device communicates with it. Nobody else can use it. And that base station may only cost you $300. There's no monthly fee. You're using unlicensed spectrum. You can install it anywhere. Now, the advantage of a public one, which is where a cell tower is installed, for example, it only works where the base station is, but you don't need to install a base station, and you can roam. You go from place to place and it's available, except where there's no tower. It uses licensed spectrum, and so there's a monthly charge, and simply because it's public, there's a monthly charge to pay for the equipment. So let's take a look at another important factor, and that's the power compared to different IoT capabilities. So again, I've got Bluetooth LE4, and I've got Zigbee and Bluetooth LE mesh. If you look in the upper left corner, where it's very low data rates and very low transmission distances, the power is very small. So LoRa, Sigfox, NB-IoT, LTE-M, they're all very small, less than 0.5 milliwatt. That's very small power. Now, the real applications for LoRa, Sigfox, NB-IoT, and LTE-M is to go to a cell tower, which is typically 1 kilometer or more. And there you'll see at the lower left that the power is more like 20 milliwatts. That's getting to be significant. But what's really important to notice is if you want to use the higher speeds that some of these can use, you can be in the 100 to 500 milliwatt range. This is the kind of power that a cell phone uses. And a cell phone has a pretty big battery that doesn't last very long if it's being used at full speed. So this is not really practical. It can be done in bursts, but typically you don't do it. So I could spend a long time on this, but I'm going to move on, and let's talk about cost. Now, this cost data is old. This is 2 years ago, and it's been coming down. So you can see even 2 years ago, it was on the order of $1 a month for the public networks, and even as low as 15 cents a month. By now, it's quite a bit less than this. And you can see the infrastructure for LoRa, putting in your own base station, around $300. The others, it's already there. So now let's switch over and talk about availability. Now this is changing quickly, but I've got some recent data. There are 4 US carriers currently deploying 5G. Of course, you need a 5G phone or device, and you're not going to find coverage in rural areas, and you're going to find limited speed depending upon which carrier you've got, or limited coverage depending upon the carrier. So here are some. I've got 2 screens to show you, and I've thrown in some that are international. So SK Telecom is in Korea. So AT&T, you can get up to 1.8 gigabits per second. This was reported by PC Magazine. The limitation here is, in order to get that speed, they had AT&T take the tester to a location where it would work. Because as recently as November, when this data was taken, there weren't very many places where you could get that. Or sorry, this was June. This is measured in June. Now, they offer the low band, and you're going to get much lower speed, but it's going to have much better coverage. Verizon, 1.3 gigabits per second, but same issue, only in very limited areas. The latencies, you can see they're good, but they're not outstanding. And then we'll switch over here to, you can see T-Mobile and Sprint, as well as a provider in Australia and the UK. Now these providers are not offering much of the high band. T-Mobile at 583 megabits per second. I don't know which band that was. It had to be, couldn't have been the 600 megahertz band. That doesn't happen in low band. So it had to be in the high band. So there you are with the millimeter wave band, and they only measured 583 megabits per second. Sprint, similar, about half a, 484 megabits per second. This would be, couldn't be in the 800 megahertz band, had to be in either the 1.9 gigahertz or 2.5 gigahertz, mid-band. So that's a good speed for the mid-band. Now, where can you get it? Now, this data is as of November. So it's already a few months old, and it's changing fast. But Sprint in November had only 9 cities in the country and only 1 city in California. Verizon had 25 cities in the US and only 2 cities in California. At the time, AT&T was the only one to cover San Jose and San Francisco, 30 in the whole country. And if it says San Francisco and San Jose, I don't know how many cities in between are covered. And then T-Mobile, 47 cities, but only 2 in California. Now,
Well,
definitely has changed. Yes.
if you can go back to slides 30 and 31, are the measured latencies one-way or two-way?
Good question. I don't know the answer to that. Typically, latency is measured as one way, but if you're actually measuring it, you can't measure it unless you see both directions. So I have a suspicion that these latencies were actually 2-directional. Now, the 1.2 millisecond claimed, that's not measured. So good question. I wish I had a better answer. So if you're going to be installing 5G technology or designing a device with 5G, particularly for IoT, make sure you've mapped your technical and commercial requirements against what's available technically. There are a lot of different technologies with varying capabilities and costs and availability. So if you need help, Voler can do that. This is what we're experts in, IoT and wearable devices. And thank you very much. And now I'll open up for further questions.
Walter, quick question on the physical layer. What are the core technology for 5G as currently being designed? The reason I'm asking that question is, let's say if you're looking at the Wi-Fi, if you're looking at the Wi-Fi 11 AX, and also, or sometimes even people call them Wi-Fi 6 and Wi-Fi 6 enhanced, they can currently achieve peak data throughput over 6.7 gigabits per second with, let's say, 8 special stream and OFDMA. Now, is a 5G in this definition use Wi-Fi 6 or Wi-Fi 6 enhanced, or there are different radio standard? Are they also based on OFDMA and MIMO technology?
Okay, keep in mind that this is cellular. So this is going to cell towers. This is not Wi-Fi. Wi-Fi is going to Wi-Fi hotspots. So this is different from Wi-Fi.
So that means, is that to say the radio technology being used here in physical layer is also based on OFDMA and MIMO, perhaps a massive MIMO? Can you touch on
sure. that? I'm sorry, I'm not able to answer that. My team would have an answer. So what I'd recommend, send me an email and I'll be happy to get an answer for you.
Okay, thanks.
Any other questions?
Related to latency standard, has the standard currently specify the latency subgroup? In other words, what latency is being allocated for propagation delay, what part of latency is a circuitry delay, and what part of latency is allocated for network delay?
So when they're talking about latency, all the figures that I've given, particularly for the ultra reliable low latency, they didn't include any network delay. Now, when you're talking about a 1 millisecond delay, and when you're talking about a very short distance, let's say 300 meters, the transmission delay is negligible. So it's all in the radio. When you're talking about transmitting across the country, the transmission delay is the majority of it. So I hope that answers your question.
Yes, there also another level of delay is due to signal processing. For example, most of the radio, packet-based radio, you have a DSP processor involved, and also error correction algorithm. Those are also taking time. So if a standard, let's say, define what is the maximum of available latency then that helps guide the device manufacturer design their chips and the subsystem. Can you?
Yeah, so 5G has been designed for low latency, but as you can see, it depends so much on the application as to what latency you're going to get. How far you're transmitting? Are you including latency through the internet? There's many variables. So latency is not a simple question with a simple answer.
Walt, I have several questions from the audience.
Okay.
How waves from 5G can interfere with weather satellites if the coverage for this type of waves is less than 1,000 feet?
That's a very good question. Yes. So the signals that the satellites are picking up are very, very small signals. And even though the cell towers are not aiming up at the sky and they're trying not to interfere, their signals are so many times larger that they will be picked up by the satellites. At least this is what I've read. So, you know, we're talking about many, many orders of magnitude difference in the power. So the devices that are trying to pick up these signals won't be able to pick them up well enough to get a usable signal at high speed, but the satellites will actually have interference.
And the second question, thank you, Walt, for that. The second question is, based on all of these limitations you've presented, why the hype by all the wireless providers about 5G? Is it a matter of rollout strategy before all features can be realized?
Yeah, well, it's understandable why people will tell you only the good parts and avoid talking about the limitations. That's always going to happen. Many of the limitations will be reduced as the rollout happens. You know, if you're only in 25 cities in the US, that's not very good coverage. That's changing rapidly. So that will change. The one that I don't see how they're going to overcome is how do you provide millimeter wave service in a rural area or even in a suburban area? I don't see that ever happening. Now, I do have to admit that sometimes things happen that I can't foresee. My vision of the future is imperfect, but for the time being, where you can expect the millimeter wave bands and the ultra high frequencies would be either in a dense urban area or in a facility such as an entertainment facility.
Thank you, Walt, and thank you for everyone who's attended. We're going to send a copy of this recorded webinar to you and also invite you to ask any additional questions by reaching out to Walt. And if anyone wants a copy of the chat question and answers, we absolutely will have that provided for you as well. And it looks like we have a couple more questions, Walt.
Okay.
Some 5G network providers have talked about deploying compute capacity in the field to reduce round trip times. Is this really happening anytime soon?
I don't know the answer to that. The deployment is something that's changing quickly. I do have a bit of an answer. There's a service provider whose name I can't remember that operates in San Francisco, and they, even under 4G, what they offer is a cellular connection to their server so that you can have very low latency connections to a server. It's designed for people in San Francisco to get millisecond connections to a server. So there are companies doing things like that, and I expect there will be more demands in the future. Now, some applications don't even need low latency, so that wouldn't matter, but there's an awful lot of applications like connection to the server where low latency is important. So I expect things to change. And it depends upon how far you have to go. So if a service can reduce the distance that needs to be traveled, then you can reduce the latency.
Additional question, what kind of professionals will be or are in demand due to 5G development? Thank you.
Oh, excellent question. I would say that for the electronic design is largely done. 5G, the chips are available, the equipment, we've got a generation of them designed and they're available to purchase. Where the interesting things will happen will be in the applications of 5G. And it's difficult for me to see what's going to happen in the future, just as when 4G came out, things happened that were very hard to foresee. But you can see a little bit of it. For example, the ultra reliable low latency is a new segment that hasn't been available before. And I could see all kinds of possible things could happen. And I mentioned some of them in the talk. So that would be a very interesting area. And boy, I wish I could foresee the future better and tell you what kind of people are really going to be needed. But it will be in the applications of 5G, not in the building out of 5G. But it could be in medicine, it could be in transportation, it could be in consumer products. I think there's going to be a lot of interesting areas that come out of 5G.
Thank you, Walt. We appreciate the presentation today, and we look forward to staying in touch with all of the members that joined and wish you all a wonderful afternoon. Please stay in touch with us.
Thank you. I've enjoyed being able to present and having some good questions. Thank you very much.
Thank you.
Thank you very much.
Thank you. Stay safe.
Yes.